faithfully conveying value and interpreting great books from around the world. Hello, this is Sally's Book Talk. Today, the book we're interpreting for you is Failed Evolution, with the subtitle The Price Humans Paid for Upright Walking. Do you know what unique body structures humans have? Feel free to leave comments and share your thoughts on evolution. The word evolution often gives a sense of constant progress and increasing perfection. In fact, to some extent that's true, and it's thanks to the power of evolution. So, hundreds of millions of years ago, fish in the ocean ventured onto land, eventually evolving into modern humans. But that doesn't mean evolution brings only benefits without costs. On the contrary, evolution can introduce new problems. The purpose of evolution isn't to pursue perfection, but to adapt to the environment. Good enough is fine. Evolution has no pre-planned direction. It relies entirely on random genetic mutations and luck to explore different paths. In this process, evolution stumbles along, taking one step at a time. Even if some changes have negative effects, they're kept if they help overall adaptation. Take humans, for example. A key difference from other animals is that we walk upright on 2 feet. On one hand, this frees our hands for tool use. On the other, it imposes a toll on the body. For instance, common issues like cold extremities or herniated discs are often blamed on genetics or lifestyle habits. And today's book will reveal the evolutionary factors behind these issues on a larger timescale. The author, Shuji Endo, graduated from the University of Tokyo's Faculty of Agriculture, was a professor at Kyoto University's Primate Research Institute, and now teaches at the University of Tokyo's Museum of Nature and Science. He's published multiple popular science books on evolution. This book has 4 chapters and 130,000 words. Though titled Failed Evolution, most content explains the principles and achievements of evolution. In the book, Endo describes how organisms achieved the evolutionary miracle of moving from ocean to land without a plan.
Endo also analyzes the profound impact of upright walking on humans.
I'll interpret it for you in 2 parts below. The book's main content. First, what are the characteristics of evolution? Second, what body structures did upright walking change in humans, and what benefits and problems did it bring? First, what are the characteristics of evolution? The author introduces 3 key characteristics. First, evolution builds upon existing body structures, meaning it doesn't create from scratch or appear out of nowhere. New body structures emerge only through gradual adjustments to existing ones. These tiny accumulated changes eventually lead to major transformations. Thus, every part of an organism's body carries traces of ancestral evolution. The author uses the lancelet's heart as an example. Lancelets have thin skin, semi-transparent bodies resembling small white fish. Though called fish, lancelets aren't true fish. They're more primitive. Fish are vertebrates, while lancelets represent transitional species between invertebrates and vertebrates. Lancelets and their relatives are ancestors of vertebrates. Biologists consider lancelets among the earliest organisms with circulatory systems. From lancelets, we see the heart's early form. Strictly speaking, lancelets lack a heart. They have cardiac muscle cells performing similar functions. These cells sit behind the gills near the abdomen, contracting autonomously to push nutrients through vessels. Functionally similar to hearts, yet modern fish hearts are complex reddish-black triangular organs. Despite structural evolution, their position remains unchanged, behind gills near abdomen, showing ancestral traces. Such cases are common in evolution. Another example outside the book. Our ears contain the middle ear connected to the oral cavity. If you pinch your nose and swallow, you'll feel eardrum pressure, another ancestral evolutionary trace. Fossil evidence shows the middle ear evolved from fish spiracles. Spiracles, respiratory organs naturally connected to the mouth, lost their breathing function when fish moved landward, developing nasal passages for efficient breathing. The spiracles evolved into hearing organs while retaining the oral connection. The second characteristic, evolution lacks long-term planning. with many structures changing function over time. Evolution has no predetermined direction. It's entirely driven by genetic mutations. If a mutation benefits survival, it's kept. If it hinders survival, it's eliminated. Over vast periods, tiny mutations accumulate, and no one can predict what the outcome will be. And many body structures serve functions far different from their original purpose, a phenomenon known in biology as pre-adaptation. The author introduces two examples of pre-adaptation. The first is bones. Without bones to support our bodies, we couldn't stand at all. We'd be like jellyfish, soft and formless. Moreover, all our movements are achieved through muscle contractions that move bones. If an arm were all muscle with no bones, even a simple bend would be impossible. But bones weren't originally meant for supporting the body or aiding muscle movement. The main component of bones is calcium phosphate, and its initial function was to store calcium phosphate. For ancient fish, phosphorus and calcium were essential minerals, but their supply wasn't always guaranteed. Take phosphorus. There's plenty in phytoplankton, but their numbers fluctuate with seasons. When they dwindle, fish may lack sufficient phosphorus. To solve this problem, fish gradually evolved the ability to store calcium phosphate. When minerals were abundant, fish stored excess calcium phosphate in their bodies. This was the earliest form of bones. When minerals were scarce, the calcium phosphate in bones would be broken down for bodily use. These bones brought unexpected benefits to fish. Based on bones, fish developed muscles attached to them, allowing finer control of swimming, more agile evasion of predators, and better hunting. Bones also provided protection in fights with other animals, enhancing fish survival rates. When fish moved onto land, bones took on the role of body support, enabling amphibians and reptiles to move flexibly on land. Activity, initially created to store minerals, this structure ultimately became key to life on land. Truly amazing how evolution's pre-adaptation works. The second example is limbs. Without limbs, animals' movements on land would be severely restricted. Fish were able to move from ocean to land relying on limb-like structures. But why did aquatic fish evolve limbs? Fish didn't know they'd live on land someday. Biologists believe limb prototypes were sophisticated fins with bones and muscles, originally evolved for better swimming flexibility. Through fossil evidence, biologists found fish just one evolutionary step away from developing limbs. This fish is called Eusthenopteron, true palm fin. Externally, Eusthenopteron. Eusthenopteron looked no different from regular fish, but its fins held secrets. Regular fish fins are thin, composed of parallel rods covered by soft membrane. But Eusthenopteron's fins were thick with supporting bones and complex muscles that could adjust bone positions, change fin shape, even rotate entire fins. With such sophisticated fins, some fish could use them as supports to haul themselves onto land for slow movement. Over millions of years, fins gradually evolved into developed limbs, enabling more flexible motion. But Eusthenopteron is long extinct, so we can't observe how its fins actually moved. Fortunately, another fish with similar fins exists today, the coelacanth. For decades, people thought coelacanths went extinct with Eusthenopteron during the Cretaceous. In the 1930s, live coelacanths were discovered near Comoros Islands in the Indian Ocean. Scientists observed via submarine that coelacanth fins are remarkably flexible, performing complex motions, even rotating to maintain position against currents. Studying coelacanths led biologists to develop the fin-to-limb evolution theory. The third characteristic, evolution offers multiple pathways to achieve functions. Different organisms evolve distinct structures for similar purposes. The book cites birds and bats, distant species where bats, the only flying mammals, evolved flight differently from birds. Biologists believe birds descended from dinosaurs, while bats evolved from small mole-like animals. Over vast history, both evolved flight wings and related body structures. But due to different evolutionary paths, their body structures differ significantly in three key ways. First difference, wing bone structure. Bird wings have simple designs with three elongated segments, shoulder to elbow, elbow to wrist, and wrist bones. Imagine if human palms and fingers fused into one elongated bone. Our arm structure would resemble bird wings. Bat wings also have 3 segments. The first 2 resemble birds, but wrist bones differ dramatically. Birds have one elongated wrist bone, while bats have multiple elongated finger bones at the wrist. If human fingers lengthened several times, they'd resemble bat wrists. More wrist bones make bat wings flexible, bending and folding freely. Compact when resting, they expand into large surfaces when spread. This flexibility enables bats to swiftly alter flight angles and direction. Second difference, wing composition. Beyond bones and muscles, bird wings consist mostly of feathers. Feathers are crucial. They generate lift by moving air, enabling flight. Bats lack feathers. Their wings are skin muscle membranes, preventing lift generation through flapping. Bats glide more than fly, leaping from heights, spreading wings to ride winds. Third difference, hind limb function. Birds primarily flap with forelimb muscles. Hind limbs don't assist flight, freeing them to evolve other functions, most commonly for walking and swimming. Some birds have highly developed hind limbs, like ostriches whose wings lost flight capability, but legs achieve remarkable speeds. Unlike birds, bat hind limbs actively participate in flight. Their wings connect directly to hind limbs. When flapping wings, hind limbs must coordinate since their function is entirely devoted to flight. Bats can't evolve robust legs like birds. Bat hind limbs can't support body weight or walk. Some might have seen bats crawling, but that's powered by forelimbs. Hind limbs aren't used. Okay, let's summarize here. Part 1 covered 3 evolutionary characteristics. First, evolution builds on existing structures, never creates from nothing. Every body part retains ancestral traces. Second, no long-term planning. Functions change over time. Bones meant for mineral storage became body supports. Fins for agile swimming turned into land-adapted limbs. Third, different organisms evolved distinct structures for similar functions. Birds and bats both fly with wings, but their body structures differ greatly. That covers evolution's characteristics. Now, part 2. Using upright walking as an example, we'll see what body structures evolution changed in humans and the benefits and problems it brought. First, how did humans learn to walk upright? Human ancestors were African hominoids. Tens of millions of years ago, Africa was pristine forest where hominoids lived in trees. They navigated unstable branches, maintaining balance while foraging in treetops. This lifestyle honed hominoid brains and nerves, developing dexterous hands and superb balance, pre-adapting them for upright walking. Like modern analogy, though quadrupedal movers, they often stand bipedally to free hands for eating and occasionally walk on 2 legs. Why did hominoids start walking upright? Scientists don't have a definitive answer yet. A popular hypothesis. Around 10 to 5 million years ago, Africa entered prolonged drought. Forests withered, grasslands expanded, forcing hominoids down to start savanna life. On grasslands, upright walking offered advantages, like dramatically expanding sightlines to spot predators earlier. Some scientists also believe upright walking reduces sun-exposed body area, aiding heat regulation. Thus, over millions of years, hominoids gradually evolved into upright walking early humans. During this process, hominoid body structures underwent numerous adaptations for bipedalism. The author focuses on foot and pelvic transformations. First, feet. Humans exhibit multiple bipedal adaptations compared to other primates. 2 key features highlighted here. First, human heels comprise a large proportion of the foot. The author compared human feet with 16 primate species. Data shows human heel bones exceed 50% of total foot length, while most primates are under 40%. During upright stance, body weight concentrates on heels. Larger heels enhance weight support and balance. Second feature, humans uniquely have longer big toes than middle toes among primates. When walking, we push off with the big toe. Its size provides thrust to shift weight between feet. Now to pelvic changes. Transitioning from quadrupedal to bipedal posture rotated gravity's pull on organs by 90 degrees. Gravity causes organs to sag toward the lower body. Human pelvises adapted to solve this. The pelvis is a complex structure of multiple bones. Hip bones, ilium, and hominoids were tall and flat, like vertical planks. Human ilium shortened vertically while expanding horizontally, increasing organ contact area.
Thus, human pelvises became cup-like structures, cradling organs from below.
Ilian expansion also allows larger muscle attachments for powerful leg movements. Quadrupeds maintain under 180-degree leg-abdomen angles during movement, but humans achieve 180 degrees while standing.
Walking often exceeds 180 degrees in humans.
In other words, to quadrupeds, our walking posture would be like them swinging their legs toward the sky.
Such a wide range of motion. Quadrupedal bodies can't achieve this. Only humans, with broader ilia and stronger glutes, can swing legs backward extensively. Additionally, human femurs embed deeper into the pelvis. This securely anchors femurs to prevent dislocation during vigorous movement. These examples show how humans adapted for bipedalism, which brought unexpected benefits. The author believes upright walking's greatest significance was advancing hand evolution, leading to larger, smarter brains. After becoming bipedal, humans increasingly used hands for foraging and hunting, enhancing dexterity. During this process, hands evolved a revolutionary ability. The book calls it opposable thumbs. Humans can rotate thumbs to touch fingertips directly.
This enables tool gripping. Sounds simple, but humans are Earth's only species capable of this.
Other animals grasp objects, but don't rotate thumbs. They cradle items with palms and fingers. Far less flexible or secure than human grip.
This capability comes from a specialized joint between thumb and wrist bones.
Biologists term it the saddle joint. Like a horse's saddle, this joint lets thumb bones flex, extend, and rotate, enabling precise tool grip and manipulation. Over time, humans began crafting tools. To better use and make tools, our brains grew larger and more complex, making humans Earth's smartest species. Fossil analysis shows our hominoid ancestors 3.5 million years ago had approximately 400 milliliters brain volume, similar to chimps, while modern humans average 1,400 milliliters, over 3 times larger. Scientists attribute this brain expansion largely to tool use and manufacture, developing physiological and cognitive evolution. Beyond developing smarter brains, upright walking was also essential for human language development. After adopting upright posture, human larynxes descended due to gravity, creating cavities around the throat. These cavities allowed humans to vibrate air with muscle movements, producing nuanced sounds. However, evolution also brought us some problems.
As mentioned earlier, evolution builds on existing structures. No matter how adjusted, original frameworks aren't completely discarded.
Moreover, humans have only been upright for about 5 million years. Evolutionarily speaking, this isn't long enough. Many body structures haven't adapted to bipedalism, leading to health issues. The author introduces 3 health problems linked to upright walking. First, blood supply issues. In quadrupeds, blood flows horizontally from hearts, but upright humans stand vertically, creating a waterfall in circulation. The brain, consuming 14% of blood flow, faces unique challenges. Hearts must fight gravity to pump blood vertically to brains, far harder than horizontal delivery. Yet human hearts aren't significantly more powerful than other quadrupeds.
Sheep, similar in weight to adults, have comparable heart rate, pulse rate, and blood pressure to humans. Thus, maintaining brain blood supply is actually quite taxing for human hearts.
Therefore, humans are more prone to cerebral blood supply issues than quadrupeds. When overworked or hungry, people may experience weakness, dizziness, or even fainting. Beyond brain supply issues, another common circulation problem is cold extremities. Quadrupeds have limbs perpendicular to ground, but bodies horizontal. Upright humans have both body and limbs perpendicular. Blood returning from limbs must overcome gravity over longer distances, slowing circulation. When limb blood doesn't return promptly, it loses heat rapidly, causing cold hands and feet. In winter, blood loses heat faster, making cold extremities more common. Related to upright walking, the second health issue is herniated discs. Quadrupeds have spines parallel to the ground, with weight evenly distributed
across different spinal regions, but after humans became bipedal, body weight concentrated on the lower body, naturally increasing lumbar spine pressure.
Moreover, many office workers now sit leaning forward, which puts even greater pressure on the lumbar spine. Over time, the tissue between vertebrae, intervertebral discs, protrudes. The author makes an analogy: vertebrae are sandwich bread, discs are the filling. When bread experiences more pressure, the filling naturally squeezes out.
Without upright walking, herniated disc risk would decrease significantly.
The third health issue is shoulder pain. Typically, shoulder pain occurs mainly in the trapezius muscle.
The trapezius connects the neck and shoulders.
For quadrupeds, the trapezius primarily controls shoulder movement. During movement, trapezius contracts to move shoulders and forelimbs. When stationary, it rests. But after humans stood upright, the entire head's weight fall onto the shoulders. Even when still, trapezius must contract to support the head. And our hands are far busier than animals' forelimbs. From phone use to eating to computer work, hands are constantly occupied. Whenever hands move, trapezius must contract. So by day's end, trapezius remains tense with insufficient rest, leading to fatigue and soreness over time. Okay, let's summarize part 2. To adapt to upright walking, human heels, big toes, and pelvises enlarged. Bipedalism brought profound benefits, advancing hand evolution, which grew brains larger and smarter. It was also essential for language development. Simultaneously, it caused health issues like poor circulation, herniated discs, and shoulder pain. At this point, failed evolution has been mostly covered.
Most content explains evolutionary principles and human benefits.
But at the book's conclusion, the author voices a concern. Perhaps upright walking's greatest flaw is gifting us brains both brilliant and foolish, capable of glorious achievements, yet simultaneously pushing humanity toward the brink of destruction. Earth formed 4.6 billion years ago. Vertebrates emerged 350 million years ago, and hominoids began upright walking just 5 million years ago. Compared to Earth's history, humanity's existence is a blink. Yet in that blink, pursuing comfort, we've caused irreversible damage. Vanishing rainforests, global warming, ozone depletion. Long-term, these issues threaten human survival.
Worse, we invented nuclear weapons. A single war could erase our species.
Many species survived tens or hundreds of millions of years.
But will humanity last that long?
The author is pessimistic. If nuclear war destroys us, it validates the title. Human evolution truly became a failure. After this episode, what new perspectives do you have on evolution?
Share your thoughts in the comments. Well, that's failed evolution.
We've interpreted it here. Reading notes are below the audio. Until next time.